not on the next test. Now, this chapter here, in all seriousness, it's probably you're going to probably find one of the most interesting. Okay. Oh, by the way, hockey team. Let's go get it. Excited? Yeah. What do you guys have tonight?
Seneca Valley.
Seneca Valley. And they're kind of a rival, aren't they, when it comes to hockey? Yeah. Okay. All right. So you'll find out that this is probably one of more people's more favorite chapters. This one is it the next one too, or just this one? I think just this one. Yeah. This one's got a lot of neat stuff in it. But first, we initially start out a little heavy in the math, and the math drops off later. Okay, then it'll become a bit more conceptual. All right, but first of all, let's get out here what it is. Oh, by the way, what's going on tomorrow? Where are you going? Cafeteria. What do you got to do? Nothing, as long as you're good, right? And I know you will be. So everything will be fine. And again, if you need that, if you feel the need that you might have to do the assignment's on your backpack. This time it's called Sub States 310, but if you pulled up Sub Regionals 33, it's the same exact thing except for the date. So I don't intend you to do it anyhow. Okay. All right. So this is going to start out a new chapter here. This is going to be chapter 7. Atomic structure. And periodicity. And so that might not sound so earth-shattering, but what you're going to find out is that what you know about the atom is very limited at this point. Okay, you probably know that there's protons and neutrons in the nucleus, and there's electrons that go around the nucleus, right? It's a bit more complicated than that. Okay, not complicated that you can't understand, just more detail to it. Okay, so we'll get through that as we go. And the funny thing is, if we're going to talk about atoms, what their structure is, we've got to talk about electromagnetic radiation. Electromagnetic radiation, or commonly referred to as EMR. We don't want to write that out every time. Okay. So, electromagnetic radiation, and I don't think I go into all this detail with you guys now. I don't, because you do some of this in physics and in integrated science. Electromagnetic radiation is all the different kind of waves that are out there. Now, your body is equipped to sense one little section of that electromagnetic radiation. What part of your body is linked to do that, or hooked up to do that?
Your eyes for visible light.
Your eyes for visible light. Okay. So if this is all the electromagnetic spectrum, you can see about that much of it with your naked eye. So really, you're missing out on most everything with your naked eye. Okay, there's a lot more information out there. If you could see it in radio waves right now, they would be all over the place. If you could see in microwaves, they'd be all over the place because they're streaming out of things like this, out of that little thing up there, that little router. They're streaming from radio stations flying through you, but those wavelengths are just so long we can't see them, right? And there's other types of wavelengths. You can sense another one of these types of wavelengths, but you can't see it. You know what that is? Comes out of that thing what those books are sitting on top of. Heat. Heat is infrared radiation. Those are wavelengths just a little too long for us to see, but we call that heat. Okay? You also can have a delayed response to a particular type of radiation, but you probably won't notice till later in the day or the next day on a very, very sunny summer day. And you might want to be fair-skinned if you want to detect it. Yeah, so what light is doing that? Ultraviolet, yeah. So that's just above what we can see, okay? And then we have ones that we can shoot through your body to see if you broke a bone. X-rays. And then we have other ones that come from nuclear bombs, or we can use to fight cancers in the brain and stuff. Gamma, yeah. And so we have all these different kinds of wavelengths out there, okay? And that's what we call the spectrum. Now, I'm not going to get too deep into that, I don't think. Oh, we'll get into spectra a little bit later. But all of those things are different types of electromagnetic radiation, which are basically radiant energy. Radiant energy, so that radiant means it's emitted, or it spreads out. Radiant energy that exhibits that exhibits a wave-like behavior. Brain, connect to the hand. Wave-like, whoa, man. Wave-like behavior. And travels at the speed of light in a vacuum. And that speed of light is pretty fast. That's 3.0 times 10 to the 8th meters per second. That's going pretty fast. So just a couple perspectives on how fast that is. That's like the sun or the moon is just over 1 light second away. Just over. The moon on average is anywhere from like, I think at the average is like about 220,000 miles. That right there is 186,000 miles. So it takes just barely over a second for light to get from the moon to the Earth. Or the sun is about how many light minutes away? Anybody know? 8? It's a little over 8. It's like 8.5 or 8:27 or something like that. Another way to think about it is, if you got my globe up there, imagine you could stand on the equator and you had a flashlight that you could turn on and it could go around the equator. It would go around the Earth 7.5 times in 1 second. Right? So if you clicked on the light, you would see it come past you 7 times, plus it would make it halfway around the world by the time you count to 1. So it's fast, right? It's very, very, very fast, okay? Now just some little interesting things here. I thought this is interesting to give you an idea of things. Okay, so that speed I'm talking about is 186,000 miles per second. Okay, that's how fast we're going. And let's say I turn this into miles per hour, so miles into hours. I'm writing this small, it's not a big deal that you copy down the numbers. And let's say I turn hours into days. And let's say I turn days into years. And so what I could come out with is how many miles per year, or how much a light year is, okay? How much light can travel in a year. And so that's, let's see. Oh, I'm sorry. This is supposed to be not hour. This is supposed to be seconds, and this is supposed to be hours. Sorry. Okay, yeah. Well, I got this all backwards. Okay. This is hours. This is days. Days. Years. Got it all backwards. Okay. So 1 hour is 3,600 seconds. 1 day is 24 hours. 1 year, 365.25 days. And if I do all that work, I come out to 5.9 times 10 to the 12th. So we're going about close to 6 trillion miles a year. That's how fast light can travel. Okay, so the light emitting from the sun right now, if you found out where that light was, that energy was, 1 year from now, it'd be about 6 trillion miles away, which is pretty far. Be a light year away. Okay, so this is the speed of light, right here. Okay, now for this calculation, I'm going to do fastest object ever created by man. And what it is a Juno. It's a Juno spacecraft that's going to Jupiter. Okay, I think it's currently on the way there, and it's traveling at a speed of 25 miles per second. Pretty fast, right? I mean, it's going across Erie County, maybe from Ohio to New York state line in almost a second. That's about that kind of distance. All right, well, let's get rid of seconds and go to hours. Let's get rid of hours and go to days. Let's get rid of days and go to years. And that'll give us how fast that object goes in terms of miles per year. Okay, so we got our 1 hour is 3,600 seconds. 1 day is 24 hours. Our 1 year is 365.25. And when I calculate that, I get 7.9 times 10 to the 8th, which is a pretty big number. Okay. It's a pretty big number. But if I take those two numbers and divide, I can turn this into a percent. Okay? So if I take 5.9 times 10 to the 12th, not other way around, I want to do that clear. I want to do, if I take 7.9 times 10 to the 8th, and I divide that by 5.9 times 10 to the 12th, and then I multiply that by 100, what I'm getting is the percent, the percent that this is of the speed of light. Just like I do your grade, right? You take your points over the total points times 100, that gives you a percentage. This right here is 0.01, 1/100th of 1% of the speed of light. 1/100th of 1%. Or you could say it's 1/10,000th the speed of light. Okay? So what it can take light to travel in a year, it would take our fastest object that's possible, how long?
1 million years?
Not a million. How much? Close. 10,000. So think about that. What light can travel in a year, if you can travel at the speed of light, it takes us, our fastest object ever, 10,000 times longer to do it. So if it takes 4 light years to get to the closest star, how long is it going to take our object to get to the closest star? 40,000 years. That's a couple generations, you know? So
have to freeze people.
yeah, they'd have to do something, yeah. And the other thing is this too. The other thing is too is you got to feed the people too, you know. So you got to come up with a way. I mean, it's a real problem.
Got dead bodies.
Yeah.
If something was like if they're running a spaceship going faster than the speed of light,
Can't go faster than the speed of light.
like just theoretically,
Can't.
Sit down.
Here's why. You want to understand why?
Yeah.
This is a very simple explanation. All right. As you approach the speed of light, people looking at you, not you, but people looking at you see your clock go slower and slower and slower as you go faster and faster and faster. Okay? So let's say now that your clock to them appears to stop at the speed of light. That means you can get anywhere in no time. You can't go faster than that. That need explanation?
Time's just a human element, though.
No, it's not. No. It's not a human element. It's not, no, it's independent of humans.
I think it's relative to humans.
It's relative to everything.
I think, but if life is never ending, I don't think it's relevant to that. It wouldn't matter.
I would say you're wrong.
I don't know.
No, I do know.
I think you can go back in time.
You cannot. But
Time-
see,
time
what are you
still
basing
happens
this on?
just
I'm basing this off a lot of studies.
If you're going
You
so
obviously
fast,
never
the time's
watched
going to stop.
cartoons.
If you could go faster, then you could.
It doesn't work that way.
Time will always go because the universe just has time. Our ways of measuring it are a human element, but
Yes.
but time
I
just
don't know. I
happens.
think someday they'll be able to prove one or the other. Like,
Oh yeah.
Okay. Well, you keep studying because I think you're wrong. Put it this way, I know you are. I'm not trying to be mean. I'm just saying it's not correct.
so that page on Twitter about
You can trust me or not. I mean, I'm well versed on the subject.
I think someday it's going to be possible.
No.
Nope, you're wrong.
I mean, I'm sorry. It's just
I got a question.
arrow time's a one-directional thing. There's nothing in physics. There's some mathematics that say it can go the other way, but there's many times mathematics say things that are possible mathematically but aren't possible in reality. Just saying.
So if you're going at the speed of light, it uses no time.
Somebody looking at you sees you go in no time. You can't go back in time.
Back to the Future,
How does-
man.
No, it's a movie.
If you could have negative particles, you could have negative space and negative
Are you
pressure.
going so fast that your clock slows down? What does that mean?
No. It's called. Okay. All right. Do you guys want to digress and we won't get into as much homework?
Yeah, sure.
Okay. Now look. I think there's a lot of ways to do this. Here's one way. And I haven't described it this way in a while, so forgive me if I need a couple seconds to figure this out. Let's say, for argument's sake, that I am in a ship. Okay? And in that ship, I'm sitting there, and to me, the ship's not moving. Okay? And let's say I have a clock. But the way my clock works is that I have a light beam that bounces up and down. off of two mirrors. You follow me? So this is a mirror up here, this is a mirror up here. And the way that I measure time is, in 1 second, that light beam should go so many times back and forth. You with me? Okay. And so that path of light that it travels is going to be the distance of 1 light second. The distance that light travels in 1 second. You with me? Okay. Now, let's say somebody is watching you from the outside. And they're standing here, watching you. Now, here, you were standing here, watching your own light beam go up and down, up and down, up and down. And it doesn't matter if you're moving or not, you're stationary compared to the ship that you're in. Okay? Now let's say this light beam's going up and down. So it's going to go up and down. So at one point it'll be here, at one point it'll be here, at one point it'll be here because it's going up and down. To the outside observer, what they see is the light beam taking that path. Follow me? That's a longer path than that one.
Whoa.
Okay? It's a longer path. From this guy's perspective, this light beam seems to be going a lot further when it goes up and down one time than this one. Speed of light is fixed. If the speed of light is fixed, and this one went further, the clock must be going faster. Let me see. Slower. Slower. Wait, I gotta get that right. See, this is where I gotta think through. This is the explanation. Okay. When this guy looks at this here, yeah. This has gone a longer distance, so time must be going slower to get further. You get what I'm saying?
Vice versa, opposite. Vice versa.
Yeah. Now, let's think about the guy that's on the ship, okay? Well, now let's say his clock, well, it works the same way, but if he had his clock here and it was going up and down, right? As I go past this guy, everything seems normal to me, but now this guy seems to be, relative to me, he seems to be moving faster. Because I'm just standing my ship, everything looks normal. He looks like he's zipping past me, when really I'm zipping past him. It's the same thing the other way around. For me, his clock looks like it's going actually faster.
Yeah.
I have to say, his clock looks like it's going faster. Do you follow this? And it all comes down to this. The speed of light is fixed. That's one of the things that Einstein figured out, is that from all points of view, light always appears to be going the speed of light. Light always appears to every observer. And so what can happen is this is something that we find out in deeper studies too, is that one of the reasons that we know that the universe is expanding faster and faster is because when you look at an object, okay, we can see it and it's got a certain amount of color to it, whatever the color may be. The faster it moves away from you, the more that those waves get stretched out. You follow me? They get stretched. It's called redshift. It's the same thing you hear, but it's the same thing but similar. It's a little different because it's not sound. But it's the same thing as like when an ambulance approaches you and you hear the pitch lift up, lift up, lift up, and then when it goes past you, it drops. Because what's happening as it comes closer and closer to you, the wavelengths are getting scrunched up. So you get higher pitch. And as it goes away from you, or like a train, the waves spread out as it's receding. Because if I send off a light wave like this and I'm stationary, then it sends off like that. But if I'm receding and I send off that light wave, okay, it's still got to go the same distance. Everybody's got to see it as the speed of light. So I see it as coming off the speed of light, even though I'm, like, think about it. If I'm standing here like this and I send off a ray, it goes off. But now let's say my object is moving in this direction and I send off the ray, okay? The ray is still going to go the speed of light, not minus my speed. It's like, if I go like this, if I take this and I throw this, it goes a speed. But now if I'm moving at the same time and I throw this, it appears to go a slower speed. Light doesn't work like that. Light isn't dependent on me, the object. Light is always traveling at the same speed. So to me, it looks like it goes the speed of light. To you, it looks like it goes the speed of light. So for one object, it seems like it got redder, and one object, it seems like it got bluer. I don't know if you get that, but... Anybody with me?
Yeah, it's
Okay. All right. So anyhow, yeah. So there's some freaky things. If you want to learn some freaky things, go ahead, check out some videos on Einstein and relativity, and you can find some cool stuff.